Hello, my name is Varun and I am the final year computer engineering student and also the project manager and software developer for this project.
My name is Manfred Aaron Lopez. I'm a final year computer engineering student and I'm the design specialist and architect for this project.
Hi, my name is Tara Kaduri. I'm a final year computer engineering student. I'm responsible for implementation of our setup and the overall functionality.
I'm Ryan. I'm a final year computer engineering student. I'm the software developer and tester of this project.
Wouldn't it be great if cameras could communicate and share information with each other? Well, this can be precisely achieved by our distributed topology method, as opposed to the conventional centralized approach. More specifically, we track moving targets in single and subsequently multiple video footages on a global reference frame. Now that's a smart surveillance system. In our project, each camera is treated as an individual processing node, which eliminates the need to have a local fusion center. The estimates recorded by the cameras are then shared amongst each other to arrive at a global analysis of the scene. The overall system design is constituted of three main phases: correlating views, target tracking, and real-time processing. As you can see, a blueprint of our design includes two cameras with partially overlapping coverage areas overlooking targets appearing in their fields of view. It is important that targets cross over at some point. The tracking aspect involves detecting targets on their very first appearances in a view. Next, through background subtraction, pixels were assigned values depending on whether they correspond to the background or the foreground. Pixels that corresponded to the foreground were assigned a value of 1, which is associated with white, and the pixels corresponding to the background are assigned value 0, which is associated with black in the picture shown. Blob analysis and Kalman filtering help in binding the target in a bounding box and predicting its trajectory. Associated tracks are then displayed based on the target's position.
In this project, two cameras with 20% overlap in their view are used. We take the corresponding point of the two views by using the checkerboard. These coordinate points are extracted from the center of the black square in the checkerboard, and these points are passed to the algorithm that determines the homography matrix.
To correlate two different camera views, we used homography matrix that relates points from two different cameras. We used the ransack algorithm to obtain homography matrix. To get more accurate answer, we ran the ransack algorithm 100 times and took average.
The final phase of our project is real-time processing. In this phase, we obtain and process live feed from two cameras. Then we use the homography matrix to create a global reference frame. Finally, we assign the same tracking ID to targets when entering another view. As you can see in this video, the target at the bottom maintains the same tracking ID when crossing from one view to another. The same happens to the target on top. This video shows the tracking of targets in the global view. It can be seen how each person always maintains the same tracking ID.
Our results are consistent with our expectation in that we managed to successfully track a moving target in single view with very limited influence of shadows. We found the algorithm perfectly tracks more than one target even if they are close to one another. We also created a global reference video that tracks the moving targets in two different views live. We found the transition of moving targets in different views smooth and lag-free.
Two of the prominent challenges are floor mapping and camera panning. Floor mapping is a tedious exercise, and sometimes this exercise has to be repeated to get accurate values. Camera panning needs a high degree of precision during calibration for successful implementation. The project is unique because we've been able to identify a moving target in two different views with high degree of accuracy and extend the functionality to dynamic live environment.
Imagine that one target had just been identified, for example, using face recognition. Now imagine this target moves to another camera view, but is now facing backwards. Our algorithm will still allow to keep track of this target since it doesn't depend on features or position. For future work, we are planning to improve the algorithm to decrease the effect that shadows have on the drawing of the bounding box. We're also planning to increase the accuracy of successful detection from one view to another and automate the process of obtaining point correspondences.